कर दिया.
Today's topic is going to be irrational principles, irrational concepts, game theory, and financial methods.
Thank you. Hanji. For rational route for irrational markets, let's start with tulip mania. 1637, Dutch ruled the world, most powerful, prosperous economy. And these guys were obsessed with tulips which were broken. Like instead of having the complete bulb, just some petals off. And like basically the rulers wanted such tulips to show to their guests that we can find rare tulips. So people just started buying tulips and selling it to other people. The Viceroy tulip became the most prized variety. At its peak, one Viceroy tulip was traded for 4 pigs, 4 oxen, 12 sheep, 24 tons of wheat, 48 tons of rye, 2 hogsheads of wine, 4 barrels of beer, 2 tons of butter, 1,000 pounds of cheese, a silver cup, cloths, a bed with bedding, and a ship. Yes. For one. No. For one. Someone gave 1 tulip to someone and the other person gave this much. Stock traders jumped in, their equivalent of traders, believing prices would rise forever. People bought tulips on debt, assuming frenzy would never end. We reach something called max stupid. We'll define this word very formally in a few moments, but I think the word tells you more about what it means. Debts came due and no one wanted to buy tulips. People just were taking loans. No one wants to buy a tulip at that high of a price. The market collapsed. Many were bankrupt. Yeah. History often repeats itself. We have seen countless bubbles. Dot-com bubble, startup bubble of 2010s, NFT crave of 2020s, startup bubble. You cannot lose money to make money. Fundamental rule of life. You can't say, guys, I'm losing $1 billion nerve, tomorrow I'll make 2 billion. How? On what basis? NFT. A monkey you drew while half asleep is not worth a Picasso. I think we all can see through all that, right? We don't believe that a monkey drew on paper is worth more than Picasso. And like, I still don't understand why this happened. It's dumb. It's just dumb. Don't trade in non-fungible tokens. Before that was a word, it was a common advice given that do not buy things which are not tradable. Money is fungible. Your 500 rupees, my 500 rupees are worth the same amount any day of the week. Your monkey and my monkey may not be worth the same amount. The big question is, why do bubbles form? Why do they inevitably burst? This talk will dive into game theory to uncover the psychology behind speculative frenzies, strategies that drive bubbles, and the tipping points when rationality returns. Because I just wanted to point out the dot-com bubble because all of us were not born yet. There was this company called pets.com. They used to ship pet food for loss. Their tagline was, because pets can't drive. They have to just ship pet food at loss, clear loss. Yeah. This is at the peak of the bubble, $14. This is where it is now. 0.64 cents. Yeah. You can see how well inflated it was. There was Enron. Enron was a power company. What will a power company do? Give power to people, supply power lines, make power bridges. Yeah, they decided to give people CDs. Distribute CDs to each other. They became a media streaming company all of a sudden. And somehow people liked it. Before they didn't. This was the guy who caused this bubble to happen, Mr. Gates. And this is the just copy of this guy. MicroStrategy. Yeah. And all this started from this one well-known cover, getrich.com. Times decided to tell the people that if you just put .com in your name, your stock value will triple overnight. And that was somewhat true. at least in that time, because internet had become a hype that, oh, if these guys are internet, they are doing something good. And traders just jumped on it. But unfortunately, no hype sustained forever, and it did fail. But before we can deal with any of that, we'll have to come to actual normal economics and math. Let's talk about rationality. Most of economics runs on the assumptions that everyone involved is rational. And with this is what we mean, do the best you can given how you perceive the game and how you evaluate with various possible outcomes. But in theory, but what happens in practice? Are people perfectly rational in practice? Not really. Okay. We'll just come here. Complete. Yeah. Okay. Yeah. Without any advertising, both companies are earning $5 billion a year. And the Coke market is not very big. Like, you cannot sell more than $10 billion worth of Coke. If a company spends $2 billion a year on advertising, they can capture $3 billion of the sales from their competitor. If both spend money, no one gets any new sales, and they just lose $2 billion. What will happen? Does someone want to make up? Yeah. What will happen? Why will they advertise here? Exactly. Correct. Let's say Coke decides, let's not advertise everyone. Well, Pepsi have all the incentive in the world to advertise now. And if Pepsi decides the same, Coke have all the incentive. To put it in very good terms, not advertising is dominated by advertising. If you decide to not advertise, the other party can always do better by advertising. Which means that's not going to happen. So we play the first law of game theory, we never play strictly dominated strategy. If you have a strategy and your opponent can do something to always come out better against the strategy, you do not play it. Second law, rational choice may lead to outcomes which, because as it turns out, if both of them did not advertise, they were making more money. But by being rational, by being smart, if we say it, they both will advertise and they will both not have the sales which they actually even had. They'll just lost money on that. This is clearly a version of prisoner's dilemma. Does everyone know what a prisoner's dilemma is? Yeah? Now the thing is, prisoner's dilemma does not really work in real law and order. People have tried doing it, but normally people don't snitch on each other. Could anyone try to guess why? Like, I have left this as a question, but someone else. Anyone? Hey, it's just a guess. You don't need to be correct. From a rational perspective even, let's say everyone is perfectly rational, even still people wouldn't snitch on each other. Why? Exactly. It's a repeated interaction. And secondly, once you snitch on someone and you if you don't go to jail, someone will find you and beat you up. So that's obviously a threat. But more than that, you will interact with this person again and again and again. Sometimes in repeated interactions, the rational strategy is not playing the rational strategy to some extent. Hint, look for repeated interactions. You can just Google repeated interaction games. You'll find a lot of literature. It will not be relevant to us, so I'll just pass it off as a note. Yeah, best response. Any guesses who said this when I'm again? Yeah, this is a Lincoln quote. While Lincoln is not talking about game theory, he is somewhat correct in our regards. We are not thinking of what we will do. We are thinking of what opponent will do given what they think we will do. And we are making choices like that. Let's go from one coke to another. Cocaine is controlled by oligopolies. Let's work with a small case. There are 2 cartels in the world, only 2 cartels. Everyone else have been killed or eliminated or whatnot. And everyone have 1,000 tons of cocaine, 100 tons of cocaine. Let's say the cost per gram is 200 minus Q1 minus Q2, where Q1 and Q2 are the amounts of cocaine in cartels. Now someone will point out that this does not make dimensional sense, right? Yeah, much of economics doesn't. Basically Q1 and Q2, if just the amount of cocaine which is out in the world, and as amount of cocaine increases, people are not willing to pay the price, right? Because more and more simple supply and demand. Here 200 is just a constant preventing maximum how much someone will pay for a gram of cocaine. Drug dealers and consumers don't have much loyalty. I should not call them consumers, they can be called addicts. Not really. And they will buy the cheaper cocaine. Each firm have revenue 10 power 5 QI 200 minus Q1 minus Q2. QI is which firm we are talking about. 200 10 power 5 because 1 ton of cocaine is 10 power 5 grams. Cost to produce a ton of cocaine is, let's say, $1,000. So the profit is this equation. Okay, yeah. So just with this much, we can tell you where the prices will converge. How? Let us say, what does the price converge to? Let's say my opponent is producing Q2. Let's say I'm Q1. Let's say Q1 hires me and says, guys, we need to decide how much cocaine we need to produce. My best response is to produce some Q-1. Then it is just a differentiation, right? One variable differentiation equation, simple optimization. And we'll get that best response for Q1 is to produce 50 minus Q2 by 2 minus 1 by 200 tons of cocaine. Everyone can differentiate. Yeah, sure. Yeah. If cartel 2 shuts down, let's say cartel 2 shuts down, they produce 0, then my production is just short of 50 tons. I can produce 100 tons, but I will not produce 100 tons. I'll only produce 50 even if they shut down. Let's say Q2 shut down, Q2 is 0. So my best bet is to only produce 500 yet. Just produce 50 yet. The same analysis can be made for Q2, symmetric situations, yielding a similar equation. So they will converge to a point which will name Nash equilibrium, where no one can do better. If Q1 does better, they actually produce any amount. As long as Q2 doesn't budge, Q1 makes loss, makes less profit actually. So the only thing you can do is produce this amount. Once we reach here, we will stay here. Okay, I'll just exactly tell where here is. Q1 is equal to agreed on both. Now, if I make a graph of both of them, where do we intersect? When Q2, when this just can be put there, right? Q2 equals to Q1 should be a point of intersection because symmetric equation and everything. Yeah. So if I just set Q2 is equal to Q1, which is the point of intersection, so we get something like this, 100 minus 1 by 100 divided by 3, which should be the production which both people make. This graph will look something like, not exactly. So the point is, if you go here, you just lose money. You were just making more money when you were on the point, as long as the other person is not changing the strategy. Which means this is some sort of a stalemate position. Changing strategy is not viable for anyone anymore. This is called the Carnot price. This is called the Carnot's duopoly. It was perhaps the first example of game theory ever. This was before the term came out. Carnot was an economist. So yeah. So this kind of best response Nash equilibrium. As of now, even if you know any other definition of that word, our definition of Nash equilibrium is where no one can do better by playing something else, assuming everyone else does not change. That is what we are taking as an assumption at this moment. We will define Nash equilibrium formally in a moment, but so yeah. For example, we have political candidates. Let's say candidates choose a platform, left to right. Voters are spread out along this ideology line. leftift to rightist. Simultaneous announcement of positions. Voters go for the closest candidate. Play to win the election. What do we assume will happen here? Someone from this side. What do we assume will happen? Okay. Why do you feel on the median? Okay. Correct. This is called median voter theorem. And yeah, the proof is rather that without law of generality, let's suppose P1 have more votes than P2, and that P1 is just before the median. Then P2 will deviate and choose P1 plus epsilon, where epsilon is small, so that P2 is also just before median. So what will happen is all voters will go to P2 now. All voters who are just after the median will go to P2. And because median means half people are there, at least half votes will now go to P2. Since this means P1 can do better by doing the same strategy, by adding some epsilon. And we can keep going, and eventually we reach that P1 is equal to P2 equals to median. As we proved, median voter position is dominant. It is the Nash equilibrium. You cannot really do better. Yeah. UK, there's your answer. UK, they both have almost the same views, the major parties, with difference on the executions. See, the reason for that is also there. It's called the candidate voter model. In modern democracy, to become a candidate, you don't need much effort, right? If you are a voter, becoming a candidate is not very difficult. In candidate voter models, differentiation is possible. Here we are assuming that there are some people chosen by the gods. In fact, only these guys can contest the election. I know it's a slightly weird setup, but UK does have that. Like, I agree that there are now few parties, but if you again go to the major 2-3 parties, you'll find all of them have similar ideologies with slight differentiation for execution. Why doesn't this always happen? There's deeper voting theory, which we won't cover today. There's a great AMC monograph on voting theory, AMC volume 20 if I'm correct, which covers almost all which you can get here. Yeah, there are a few more uses of this. One is called the hoteling, which tells where do people set up their hotel firms, etc. Funnily, this guy's name is also very similar to the thing he worked on. Product positioning is Lancaster, I don't know how. Yeah, sample retelling. Can someone say what will happen here? Firms choose a location on a beach. Consumers are evenly spread out along a line. Prices are fixed. Consumers buy from closest vendor. Where are our firms going? Here, I think you can tell the median. Exactly. They'll just go to 50-51, 0 to 100. They'll just go to 50-51 areas and just fit there forever. So as it turns out, firm positioning was a slightly more even version of, like, weaker result of that. It came before, obviously. Commoditization. It's a long word, but a simple concept. We have seen this when we go to a grocery store and we have a bunch of cornflakes with no difference other than one reading Kellogg's, one reading something else, one reading something else, and all telling the same thing. Ragi hai, wheat hai, pata nahi kya hai. Or when shopping for new TV and we just find 50 sets with the same film. There seems to be any noticeable difference. So what will people do? They'll just buy the cheapest product. It will, instead of being a product, it's now just a commodity. The thing is, when you buy paper, you don't see which brand ka paper, which brand am I buying? You just go to wherever you're buying and you say, give the cheapest one. Sometimes you put some quality restrictions, but you just take the cheapest on that quality. Commoditization reduces profits by bringing prices to corner prices. Please note here, if these guys were cooperating, if the cartels have come together, and decide that we don't want to compete with each other. So they can just charge more prices, make more profit individually as well. If both of them decide that we'll both put out 50-50 tons. No, like they just become one cartel. But the point is, as long as there is competition, consumers are happier. Obviously, branding can the way companies try to circumvent this without creating monopolies is by branding. A phone made by Apple doesn't need to compete with a phone made by Samsung. They can just say that no, sir, we are Apple phone, we are not competing with them. And the same thing can be said by Samsung. So technically, in the class of Apple phones, Apple have a monopoly. And technically, in the class of Samsung phones, Samsung, basically, if you make a brand out of yourself, you are the only person selling that brand. And you can charge higher prices. As I told, you can go for the branding on a line and candidate voter model. These are the two things which explain. Candidate voter model also explains why in multi-party systems, you will normally find candidates slight deviations from the median. Normally like 1/6 standard deviation from median or something is what you get on candidate voter model. It is also not completely correct. Some of the things happen due to how the voting system has been set. But yeah. Now we'll just, this is a very interesting question. Have someone seen this question before, I think? Yeah. There's a small issue. Let's say we just did best response, right? Let's say I know that you are going to do binary search. Now, can't I set my number just so that your binary search takes the maximum time to reach my number? We can do that. So now that you know I'm setting my number like that, doesn't your optimal search pattern change? Right? Yeah. Game host of trying not to lose money. Yes. The problem is that you have 5 guesses, right? Till you can make money. Well, 100 does not get binary searched on 5. 100 gets binary searched on 6 or 7. Right? So that's the issue. That means I can just set my number so that it's in that area. Now your best strategy changes, right? With the information that my strategy has changed, your strategy should change. But now that your strategy changes, won't my change again? As it turns out, this question, yeah. हाँ बोलो बोलो. Yeah, there is an equilibrium. The equilibrium was found very recently. Like Microsoft was wrong on this. They first did not consider that the host can change strategy. When they started considering that, they kept going into the loop downhole, like rabbit hole, till they removed this question out. The question was given by Steve Ballmer, who was a major guy at Microsoft at one point. Yeah. Okay. Bhai, how do you know? It is optimal to reject the challenge if your odds of actually, yeah, the odds of winning are not there. You lose money. Yes. Yes. Hmm. Uh-huh. Not no. Let us start at binary first. We can start anywhere, right? Hmm. No, as it turns out, this comes to a Nash equilibrium. You will reach one. The Nash equilibrium, if I'm correct, is where you try to do a Bayesian norm. You just assume a normal distribution of the host choices, and you just do a Bayesian search on that. And the host have a beta distribution. And the point is, any of you changing reduces payout further. Like you changing makes host win, and the host changing makes you win. The question require is like a bit too hard. It will require something which we'll do a bit later now. But as it turns out, it can be solved. If I'm correct, if I remember correctly, there's no proof of uniqueness yet. The thing is, when the computer will have to choose random strategies of however how many cases the paper used, it kept converging to the same beta and normal. So it's that is a hypothesis yet to be proven. There's no uniqueness is not proven yet. No Nash equilibrium. As it turns out, there's something called Nash theorem which guarantees that you'll always have a Nash equilibrium. Yeah. That's a guarantee given to us. So yeah, you can work on it. This requires a bit of programming as well. The original proof used something called minimax theorem and DP to do work. Yeah, Nash equilibrium. Yeah, this is the very formal definition of this word. Yep. Not a part of the model, bhai. Yeah. Coming back to our topic, Nash equilibrium are these magical stalemate points. The formal definition is given a strategy profile for agent A, agent B, and onwards, without law of generality, A1, B1, C1, dot dot dot, is a Nash equilibrium if and only if utility of choosing A1 given B1, C1 will be chosen if greater than equal to utility of choosing anything else. The definition seems clear enough. The same is true for B and C and for every other agent, right? If please note, these are not your choices. These are not your choices. This can be a strategy profile. That means they can be just a probability distribution on your choices. That's just a strategy profile. Why are we interested in Nash equilibriums? They always exist. Nash proved that in 1950. It is somewhat a reason why he got his Nobel. Easy to find for us, for firms given enough time. Nash equilibriums normally can be reduced in most games to either a tree traversal or to a linear programming question, which are both things which are solved in most cases. What do we mean by given enough time here is evolutionary game theory points. That let's say firm start at some prices, next year they change their prices based on last year prices, and they'll also eventually reach the game theoretic numbers. Which Nash equilibrium will reach? We can reach many, but normally which will reach? It is stable. By the definition of the word, Nash equilibriums are stable. No one have an incentive to deviate. The stable here means that no one have an incentive to deviate anymore. It is a tool for out of sample predictions. It is also criteria for investment decisions. They leave player with no regrets. At a Nash equilibrium, you cannot say that I could do better. You really can't, given everyone else plays that way. They are self-fulfilling and self-adjusting. Anyone moving normally will deviate back to some Nash equilibrium. Not guaranteed to be the same one, but will deviate to one of the Nash equilibriums. Limitation of Nash equilibrium. Equilibrium does not mean optimal. We saw that with the Coca-Cola case. Does not mean optimal. Many interesting games have more than one Nash equilibrium. Why if there's a star and always exists? Consider this example. Two friends want to take the same class. They are math majors, so they lack communication skills. They can choose between proof and types and measure theoretic probability. This was used last student seminar to aim at two particular people. The payoff matrix is friend one likes PNT a lot, so he'll be happier if both of them come to PNT class. So he'll be like, yeah. And the other guy is like just happy to be there with his friend and learning math. Let's say you go to the first guy goes to PNT and the other guy goes to MTP. He'll just be sad. Yeah, I did not even want to do this class and I don't even have a friend. And let's say you both go to your friend favorite class, you'll still be sad. Okay, I don't have my friend. Okay, so whatever. Do we have a Nash equilibrium here? Do we have a pure Nash equilibrium? Yeah. Okay. I will argue that it's not. We'll show that it's not. But you can do slightly better by not being a little random. Slightly better. Any guesses on the other end? What? This we've taken as player 1, this we've taken as player 2 normally. Player 1, player 2. The problem is they both lack communication skills. So they just need to choose one. They cannot communicate now. That's the issue. That's the problem here. If they had communication skills, the problem would be solved, right? So what do we do? Okay. The point is 1 by 2 will not do it. Like if you flip a coin, you need to. Yeah. How means like I need to make one choice, right? Let's say I choose PNT. Oh, there's no pure Nash equilibrium, right? You cannot just decide that choosing this strategy is best. You need to do something. However, if I choose PNT with probability P and MTP with 1 minus P, we can solve for P to find a Nash equilibrium. The point I'm saying is the Nash equilibrium is not 1 by 2. Yes. It is 1 by 3 of going to the class you don't like and 2 by 3 of going to the class you like. Yeah, I'll just come. Okay, we'll just. What? Yeah. See, we are saying that let's say there is a. We'll just prove it out. Like we'll just work it out. See, let us say that P, like the first person is choosing bad variable. First person has P chance of going to MTP, 1 minus P of going to P of going to PNT and 1 minus P of going to MTP. So we are claiming that if this is a Nash equilibrium, the other person choosing anything does not change his payoff, right? Nash equilibrium means taking any strategy cannot do better. So if I show that any of the pure strategies can't do better, can the mixed strategy do better? Logically, no. And like you can just set a linear equation in P, 1 minus P, Q, 1 minus Q and do that. But if we just take the logical sense that if this is a Nash equilibrium of playing P and 1 minus P, the other party choosing anything, choosing the pure strategy should have the same payoff. And choosing a combination of the pure strategy will continue having the same payoff. So just, if they choose PNT, the payoff is P times with a probability P2 plus with a probability 1 minus P0. And if they choose MTP, it's with 0 with a probability P plus, oh, okay. Yeah, one is up because second player, right? Now if you solve this, you get P equal to 1 by 3. Yes. No, I am saying let us say this is a Nash equilibrium, me choosing P and 1 minus P. I am claiming that whatever, either of the things my opponent chooses, the payoff remains the same. Because it's not required. It's not required. We can include it and it will still give the same result. The issue is getting Q to the calculations makes the equations harder to solve. So instead we just take the point here that like there was an observation. I don't even think there's a proof given anywhere of this, that if this is a Nash equilibrium P1 minus P, then your opponent should not have any way of doing better by choosing either of the strategies. No, Monty Hall is not a game theory problem. Okay. Like if someone have any doubts here, you can just tell. We'll need this once or twice again. So can we somewhat wrap our mind around this, that if you could do better by choosing either of them, if just choosing P and T, given that I am choosing P and 1 minus P, could do better than just choosing MTP, then you would just do that. Okay, if I think that can be a method of proof of existence of Nash equilibrium, the most well-known method is using fixed point theorem. Like you can just say that there will be one point where all the curves will get fixed, something like that, if how you said this. But the main thing we need to get from here is the algorithm for getting a Nash equilibrium given a game. Is that part doable? I am asking that much right now. Yeah. Anyone have a confusion can just tell that. Yeah. Okay. A Nash equilibrium does not mean choosing just one option. It can be a probability distribution over options. It's called a mixed equilibrium and it always exists. The reason for existence is Brouwer's fixed point theorem and hence will not be covered. What? A Nash equilibrium is 1 by 3 chance of you going. Yeah. There was 1 by 3 chance of you going to PNT, 2 by 3 of you going to MTP, 1 by 3 of, 2 by 3 of them coming to PNT and 1 by 3 of them going to MTP. This is the Nash equilibrium. How is that better than random? Okay, let's say, let's say you are player 1 and I know that you are going to randomly choose between PNT and MTP. Okay, because I want to maximize my payoff, I'll say if I choose PNT, my payoff is 1 by 2, right? Because you have a 1 by 2 chance of choosing PNT and I have a 1 and I am just choosing PNT completely. 1 by 2. If I just choose MTP completely, my payoff is 1. If you take 1 by 2, if you're flipping randomly, I am just better choosing the subject I like. It just dominates the strategy out. Yeah. with 1 by 3 choosing either of them have equal payoff, and you can do the same analysis on the other end. So the strategy becomes 1 by 3, 2 by 3, 2 by 3, 1 by 3. That's how you. I am not claiming that every time it will be symmetric. Sometimes it can have different odds on both sides. But I'm saying that odds will be such that choosing any pure strategy will not be better. Okay, let's say no pure strategy does better. A mixed strategy, if just a linear combination of pure strategy, can it do better? Like, right? You are multiplying the payoff of pure strategies with numbers less than 1. So you basically, if P1 can't do better, P2 can't do better, and let's claim, yeah, if less than both P1 and P2, right? Because Q is less than 1. This alone tells you that if your pure strategies can't. Yes, no, it's less than the max of them, right? Sorry, yeah, less than. Correct. So if your pure strategies can't do better, there's no chance of a mixed strategy doing better against another mixed strategy. Although the algorithm to find it is much more simpler. Just assign probability to non-dominated choices of A. If a choice is dominated, just remove it. If there's a choice which is strictly dominated, it should not be considered. You can consider it just computational overload. Oh. Yeah. Solve for B choices are equal, and then you can just reverse the thing on the other end, and you're done. Yeah. The major application of this is sport statistics. There is a lot of on tennis, badminton, and penalty kicks. There's very little on cricket. I don't know the reason. Like the only thing I found on cricket was this master's thesis from Colby College, and that was pretty. Like if you just go to that paper, you'll find it. You'll just become sad. कि इतना गंदा काम कौन क्यों ही करेगा. But then again, the guy openly admits that he's a Pakistan cricket fan. तो क्या कहें? Yeah, tennis, badminton, and penalty kicks. There were a lot of data. Some of them have, yeah. Yeah, given a goalkeeper have a choice to where to jump, and you have a choice to where to shoot. And it is assumed that at a higher level, goalkeeper is bounded by human reflexes, and the ball speed is much higher. So the goalkeeper have made that decision long before you took the shot. Because he have around 0.2 seconds sometimes to make that call. So he has not made the call after you hit the ball. So that is why it is modeled as an extensive game. Every paper have different data on that. But it's a mixed Nash equilibrium. How many times should you go left, right? Which the paper I was... No, there is skill, right? There is skill. Based on the skill, your payouts are different. Let's say we have this left, middle, right, left, middle, right. This is a very simplified version. Obviously, there is up, down, and all that. This can be turned into a compact game, Nash equilibrium or something. Will not go there. That's beyond. Let's say you are a great right side hitter. So your chances of hitting on right side are 0.8. And this is a zero-sum game. Actually, we call it a one-sum game because there was a probability wise, right? And let's say on left you have a 0.6. And in the middle, how much do we want? Like this is when the goalie is jumping on the left. If the goalie is jumping on the left, actually you should have 0. You should have 1. if you're a great right side hitter and the goalie have jumped on the left, will your ball is going in? If goalie have jumped to the left and you are shooting in the middle, let's say it's 0.5, 0.6, 0.4. Like I'm just creating it. And we can just create data like this. So we can model your skill through this data, right? Like let's say here left have 0.6, 0.4. Let's say right still have 0.8, 0.2. That is just modeling your skill, that you're much better at hitting in the right. And based on a player's skill, the equilibrium will keep changing. Most such papers just assume variable for everything. And they just give out a formula or thoughts. So now that a team can go through their statistics, get data on the opposing players, and figure out what their goalkeepers should do. This is the normal idea of such things. On tennis, it is about where you serve and some things like that. I don't really understand the rules of tennis that well to know that. The badminton was a recent paper, 2021 University of Waterloo paper. Pretty good. Like it generalizes to a lot of two-player games. So yeah. Let's now do a small experiment. You will not get payoff from my end, okay? This is money which you have in the imaginary sense of the mind. Itna paisa nahi hai. If you are invest, the investment fails, you lose 100 rupees. Yeah? Everyone have a binary choice. How many people do we have? 4, 8, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right, forget. 23. So, if 20 people invest, everyone's money gets increased. If they don't, the money you invest, you lose that money. Please assume that I'll give you money. I probably won't. But assume that. With that, on a count of 3, how many people want to invest? 3, 2, 1. How many are investing? Okay. Thank you. I'll collect my 100 rupees after the talk. Okay, yeah. Obviously, we can see that this is not a very good thing, right? Like a lot of people lost money here. There are two equilibria as it turns out here. One where everyone invests. If more than 90% people are investing, everyone who's not investing should just, yeah. Okay. If more than 90% people are investing, everyone who's not investing, the 3 people in this class who will not be investing that time, they should just take 50 rupees. That's just free money. And if less than 90% are investing, the 19 people who are investing should probably get their hands lowered and not give me 100 rupees. Correct? So there are 2 equilibria. Can there be more? No, right? All the other equilibria will just go down to either of these 2. The first is called Pareto dominated. Pareto just means that while both are equilibria, some equilibria are more equilibria than the others. Some equilibria are more better than others. But we often convert, but in this case, we seem to converge to the bad equilibria, where no one invests or no one gains money really, right? So this is called a coordination game. If everyone can get coordinated, it's easy to snatch money from me. An example of another coordination game in just a reverse fitting is called a bank run. Does anyone know what a bank run means? No. Correctly. Correct. Banks rely on depositors not withdrawing their money simultaneously. Banks keep around 10-12% of their cash with them and the rest money is loaned out. At least when bank runs were very common in like 150 years from now. Bank runs were like very common. But nerve, I think there are some federal laws on how much you have to keep in which liquidity and what. A law of trust can trigger massive withdrawals leading to collapse. You can just believe, okay, this is not going to work. Historic examples. Have everyone seen It's a Wonderful Life? Okay, it's a very, very famous film. It's considered a holiday classic. If any of you are planning to go to US, just watch the film before. So that if someone asks you, have you seen the film? You just say yes. If you haven't seen it, just say yes. They'll come and beat you otherwise. It won't feel good. Yeah. So the entire movie has this one guy whose bank is getting run. And he somehow convinces everyone that have trust. He does not threaten them. He does not force them. He just tells them, guys, if you all withdraw, the bank goes under and I cannot give everyone money. So you'll all lose some amount of money. But if none of you withdraw, we will be like, okay. And eventually I'll pay you. He just gets them to trust them. Obviously, he has the main character plot armor. And they trust him within 5 minutes. The point is, in most bank runs, you just need the customers to have faith for a while and not withdraw their entire money out. So here's the point. Even in our investment game, if someone can get the class to have faith that bhai, other people will put money, we should just put money. You don't need to threaten them to break their legs, right? You just can tell them, they just will. So you can get an investment done. Just for example, does anyone want to volunteer? Vedant, you are volunteering. Yeah. Vedant, you have 10 seconds to convince everyone to invest money. We'll redo the game. You have 10 seconds to convince everyone. Yeah, when 90% people are willing to. No, no, no. Let me bring it down to a little lower. Let's put it at 17. See, you don't have much to lose. So yeah, on a 3, 3 count, we'll again have to vote to invest. 3, 2, 3, 2, 1. Who all are investing money? Okay. Yeah. Weird. The rational choice is actually to invest. Yeah. More recently, we saw the first British bank run in 150 plus years when Northern Rock got bankrupted. Silicon Valley Bank got bankrupted in 23. It was yeah, it was very yeah, they got acquired. So people did not lose much money, I think. And then we had the crypto bank collapse, FTX. $6 billion, 72 hours, no real recovery have taken place yet. And we are still getting data on this Celsius $12 billion collapse, which just happened last year. I think we are roughly close to the 1-year anniversary of the collapse. This is how the scene from the movie looked. This is how an actual bank run looks. This is how Northern Rock fell. And this is how Silicon Valley Bank fell. You can see how sad people are because they're actually fearful if the money goes out. Let's talk about FTX. FTX is the first case study we have. It was by Sam Beckman. I think most of you know about a lot of this here. It was formed by Jane Street trader and MIT alumnus Sam Beckman-Fried in 2019. It was valued at 32 billion during at its peak. They had a sister company called Alameda, which was led by Sam's romantic partner and another Jane Street trader, Carolyn Ellison. Alameda functioned as a crypto hedge fund. These guys made a lot of money when Japanese Bitcoin and American Bitcoin were at different rates. They have to buy from America and sell to Japan. It's believed that they made close to $4 billion on that alone over a period of 2 or 3 years. It played a key role in providing liquidity to FTX because they are buying and selling a lot of amounts. They were the liquidity providers to some extent. And they also were doing a lot of these complex arbitrage strategies. If Bitcoin prices were different in countries or different on other trading apps and all that. FTX stored its customer funds in its own token, FTT, and relied heavily on it for collaterals. This should start ringing warning bells. If I'm running a bank, I can't take your money and store them in CMI coins. I can't just do that. There's no logical method of doing it. Especially if you can just buy CMI coin and its rate keep fluctuating whole day. Yeah. The reason this was done by FTX was because it could provide discounts and benefits by giving you FTT. Remember, issuing FTT costs them nothing. And as long as some people are trading FTT or just holding it, the bonding valuations will give it a value. Yeah, it will reduce. But the point of, let's say I have to give you 100 rupees off. I can just give you 100 FTT. Let's say it's now 99 rupees off. You got free money, but I did not lose money in this procedure, at least on paper, right? So I can issue coin. That's the issue. And yeah, this had a small issue that FTT, as because it was traded, it could fluctuate. Binance withdrew its investment in 21 because Sam Beckman and Fijay were not very good friends for some reason. Binance received a large amount of FTT as part of the buyout, and then 22 we have a leaked sheet which says that the FTX is doing some strange things with Alameda. This was sharing customer data, of not having money, and all sorts of weird strategies. FIVED said that we do not want anything to do with this company. We are liquidating FTT. Please understand, at this point, FIVED owned around 20% of all FTT. And he's saying that I'll liquidate it in one day. That is panic. And I think, and we already saw the trust evaporate about here. So yeah, Alameda had borrowed billions of dollars from FTX to cover its losses. FTX used secret backdoors to move customer funds without triggering accounting alerts. And with that, these guys tried to come out of this unscathed by saying that Binance is putting false allegations, we have not done anything. And they hire a company called CoinDesk to do their audit publicly. They tell that do not give the audit to us, give it to a news reporting station. Guess what? They were assuming that CoinDesk is incompetent. CoinDesk was not incompetent. CoinDesk found all the fraud when they did their job and gave it to a news station. And in panic, people started removing money. And the fault on Moonwave, FTX had invested 500 million in an AI startup called Anthropic. Have anyone used Cloud? CLAUDE. It's an AI. Yeah, somewhat popular. Yeah. If they were able to, if they did not do this CoinDesk thing, they would have still kept the trust. They wouldn't have gone into crisis, wouldn't have to declare bankruptcy, and Anthropic, they could have just removed their investment and just made a lot of money. Anthropic is valued close to 10 billion at this moment. So they could have just. So what do we learn from the story of these people? Don't do fraud. That's the lesson. Don't do fraud. The other lesson is don't be overconfident. Someone will otherwise do. And here is the reason why this is important to us. This is Terra. Terra was a coin closely linked to FTT. Terra depegs. Something goes wrong somewhere and Terra's bubble crashes. This is when Celsius and 3AC collapse because they were linked to Terra, and this is where FTX collapses. When everyone was riding the same bubble and Terra falls, then another coin called Luna falls, then FTT falls, and so do 3 companies. And lots and lots of money. Money which none of these 3 people own. As of now, even like as much as we praise Binance in this story, as it turns out, Binance is also now under investigation for fraud on customer funds. So yeah, this guy just recently went to jail. This was the photo he uploaded after he was bailed out. So yeah, the point is, they are like crypto is a scam. Let's talk about sequential games. The hat game. Let's play another game. I do not have a hat. Just sad. Yep. Okay. Yeah. I'll pass a paper because I don't have a hat. The first person can keep either no money, 10 rupees or 50 rupees in it. You can write 0, 10 or 50 on the paper, fold it, and pass it to the second person. The second person can open your paper, look at the amount written, and decide if they want to take that money for themselves or match the amount. Match the amount. Put in as much money as you put in. This is not poker. It's not poker, bhai. Yeah. When at the end, I'll take the cap. And if it has 20 written on it, 10 plus 10, if both of you have put 10 rupees, Then I'll give each of you 25 rupees. So you put in 10 rupees, you got 25, you made a profit of 15 rupees. If I see 100, 50 and 50, I'll give both of you 95 rupees. We will make a game tree on the moment. Let's see which two people want to volunteer on this one. Sure. You. Okay. Let's go on that side then. Okay, yeah. We'll take the two people. Yeah. You just have to write a number 10, 0, 10 or 50. If you put 10 and the other guy puts 10, you get 15 rupees extra, means other than your 10. If you write 50 and the other guy write 50, I'll give you 45, etc. Have an option to steal your money. Yes. If he wants, he can steal. Yeah. Okay. Okay. On this side, who's volunteering? Okay. Do you want to keep the amount? Okay, yeah. So yeah, we feed 10 and 10. Yeah. As it turns out, if you put 10, he put 10, both got 15, 15. Why did you not put 50? But like, even 45 is greater than 15. Okay. Yeah. What about you? Why did you, would he, if he put 50, would you steal? Okay. Yeah, for trust building. Okay, yeah. The point is, if this was a one-time thing, you shouldn't put, then you should steal. Yeah, because we'll take wherever. No, you should put in 10, right? Okay, we can make a game tree. Okay, if the first person put 0, the other person have not really anything, 0, 0 is the payout. If you put 10, you have option to match or steal. If you match 15, 15, if you steal negative 10, 10. Yes. And same, right? On the lower end, if you match, oh, fuck. If you match 45, 45, if you steal negative 50, 50, right? So the point is, we can do a backward induction here. We know the meaning of that word, right? We can start inducing from the behind of the tree. Let's look here. If I am here, what do? I can either get 50 or 45. I get 50. Right? If I am here, what do? Do I match to get 15, 15 or do I steal to get 10? Match. So now the tree for the first player can be shortened. The first player does not need to think of the second player objective, because now we actually know what the second player is going to do. Right? So now as the first player, I know that if I put 50, I'll just lose 50 rupees. If I put 10, I'll get 15 rupees. If I put 0, I don't get anything. What do I do as the first player? Exactly. So this is called a backward induction. I'm pretty sure most of you know what the word already means. For others, it's just induction from the back of the tree, from terminals to the node. The problem is adding 50 have the best payoff, right? You get 45 rupees. 15 rupees you'll only get a Maggie in them. 45 rupees you'll get a lot of things. Probably one chicken something and plus one Maggie. So much. भाई मैं भी वेज हूँ, but make the offer seem good, right? Yeah. By throwing in a 10 to begin with, they reduce their own payoff, but they lose the risk of losing all the invested capital. This game is in way similar to venture capital. Venture capitalists, at least good venture capitalists who are not betting money randomly, can have to actually think what happens if you give me the money and I take the money and fly off to Bahamas. They really need to think of that possibility. This is called a moral hazard, where you are scared that once I give you the money, your morals may go away and I may lose the money because of that. So what is a solution to this? This is a classic problem in car insurance. Let's say if a car insurance covers entirety of your car. Please note, the minute you take a car off the showroom, the car loses value. Let's say you buy a very good car, whichever you like. Which car do you like? Name one, bhai. Yeah. Let's say you buy a Ferrari. Kya? Okay, let's say you buy a Ferrari. The minute you take the Ferrari out of the parking lot, it was worth 1 crore, but now it's worth 90 lakhs. Then you drive it. Now, the point is you are insured on 1 crore. Oh, well, you have no reason to not drive it recklessly, leave it, park it anywhere. Because if anything goes wrong, you get 1 crore. You don't really care much about the vehicle. An insurance company does not want that in this. Because they don't want to give payouts. They famously don't want to give payouts. So they need to change the incentives, change the tree, so that it's a good idea. Let's see what we need to consider here. Insurance premium, recovery if the car crashes, cost of the car, probability a car crashes when you are driving recklessly, and probability a car crashes when you are driving carefully. Agreed? Are these enough? Is a question. Are these variables enough? Are these variables enough to yeah. Okay, discounting needs to be done. Okay. What else? First thing is we have to tell you that reckless driving should have a higher chance of accident than careful driving. That's the first thing we should add. Second is, I cannot charge you more premium than I am giving recovery. Otherwise, no one's taking my insurance. The discounting is a thing which I wanted to add, but the math becomes pretty dirty. Therefore, I have not confusing, it just becomes dirty. You can do it on a computer, but I would like to do it on the board. So therefore, but yeah, we shall now move to the blackboard. These kind of analysis are normally done in contract theory or policy design. They also appear time and again in risk management and investment work. But yeah, let's go to okay. Now this is basically a game tree, right? With a bit of changes on the payoff areas. Okay, let's make our tree first. Right? You can decide to either get insured or not get insured, and after that you can decide to be reckless or careless. You don't really have many. Okay. Now here's the point. What do you gain when you are like? What's your expected payout on being reckless? The probability of crashing is rho, right? Rho, and let's say you are uninsured for FAD, so you don't get any recovery and you lose the entire cost of the car. So there's a rho chance that you lose entirety of fee. So the insurance company gains nothing. and you will remove rho phi. Correct? Expected value of loss. Oh, sorry. This is on the careful side. And similarly, यहाँ पे over here we have minus kappa phi because careful. Now let's look at the insured side. If you are careful, you may never come into a crash. If you never come into a crash, the insurance company gets your premium, you lose your premium, and that's the end of the story, right? If you don't go to a crash. This happens with 1 by kappa probability. This is now when you are insured. Yeah. And then with a kappa probability, insurance company gets a premium, but they have to pay a recovery cost on that. And you get a recovery, but you have to remove your premium and your car cost on that. Correct? So what does this turn into? Premium minus kappa times recovery and minus p plus pk plus kappa minus pk. Okay. Right? We get something of this sort. Something. Now let us say you don't get into a crash. Like you are driving recklessly and we do the same analysis. The only difference is the kappa gets replaced by a rho. Correct? Correct? We are till here. Now that this part is done, we just need to change some things here and there to get our incentive correct. Let's say that you are not invested. Then what do? Do you drive carelessly or recklessly? Do you drive carefully or recklessly? Yes, because kappa is less than a rho. I've decided before. So in that case, you only go in this direction. Now here is a bit slightly harder question, that what do you do when you're insured? You get to? Yes. But the recovery amount is not known. Okay, let's just see. Let's just look at the sign of rho r minus rho. Sorry, this is not rho, this should be premium. Minus kappa r minus k minus k phi. Premium goes and we are left with rho minus k into r plus k minus rho. We'll just take minus rho minus k times cost of car. So I will drive recklessly if and only if my recovery is more than the cost of my car. Can we? I've just done a subtraction. This part is positive. If this part is positive, I'll drive recklessly. If this part is negative, I will not drive recklessly. Correct? So if let us now consider two cases. Let's say I give you if I give you recovery equal to the cost of the car. Like we have three cases, right? If I give you recovery less than the cost of car, equal or more. If I give you recovery less than the cost of car, then you drive carefully. Now if you drive carefully, then now you have to choose between negative k phi and kr minus whatever this is, minus this, right? It is rather easy to show that this is much lower, like this is lower. So you just choose this and my insurance policy gets bought. What? If they are equal, again my insurance policy gets bought, but my insurance profits are decreased. If it is greater, then my insurance policy does not even get bought. So if it turns out while just giving you more money than your car, will one make you drive recklessly? So if someone buys your insurance, I lose money. And second, well, there's a chance they just don't buy the insurance policy in the long run. They just go like, ठीक है, recklessly to drive करना. Why do I need an insurance on that? Because you're losing premium, right? Does the math follow till here? Huh. That is what you think. The point is, if the recovery is more than the cost of the car, like somewhat higher, then you will just drive recklessly, anyhow crash the car. So the chances of you driving carefully and not crashing the car and driving recklessly and crashing the car, you're just better off not buying an insurance and driving carefully. If it is infinitely more, then yes. Up to some ratio, people will. You have to pay the premium, right? You have to pay premium, right? In case of casualty and all, that's not included in the model. Our model is just not including that. Yeah. No, see, the point of it is fun driving a car at high speeds, right? We can agree on that. It is okay. Many people find thrill by riding cars on high speeds. Yeah, I have not included that. Like, you can just put it like being a bit reckless with your car can also be just parking it in bad ways, and it just get hit by something else, or leaving the locks open and it gets stolen. Some insurances cover stealing as well. We are on a Ferrari, bhai. They sometimes cover stealing. They just take a character test before that you will not steal your own car. Yep. See, I have not put the fun inside, and I'm not even putting the mortality of that in here. Yes. The row is not what you are choosing. You are choosing to drive recklessly. Row is just a fact of life. Oh, okay. Yeah, you can do that. Okay, if we assume rho equal to 1, yeah. Okay. Okay. Kappa equal to okay. Okay. In this scenario, what happens is a good P minus C. Okay. What is lower? Minus P gaya, R minus C. Okay. If you are careful, then okay, in that case, we will need to give an insurance policy greater than the value of car. If you're 100% sure to crash. Because in that case, your best strategy becomes to drive carefully if you're insured. And if you are careful when you're insured, then it's just negative P. So like, why you do pay premium? Yeah, but the point is kappa is not zero in life. That is the one thing we are adding here, is that there's a chance that you may be very careful and you may still go into an accident. Someone else hits you. Because the car costs money, right? So you are just insured. Okay, if there was no probability, yeah, obviously you'll not buy anything. Yeah, that is the, you can't assume. Yeah, you can. If rho equals to 1, then you will not, and kappa is not 0. So sometimes you're better off paying the premium. Then it becomes a question of how to set the premium amounts. Yeah, we can do that. It's just computation. If the model somewhat clear, I agree it's not a very realistic model. No model really is. This is extreme. Oh. To recall, sequential game have deficient nodes. We have action on edges and the terminals are payoff. We start a terminal deficient, move backward, etc., etc., etc. To recall, not perfect rationality has been assumed here. We are still being perfectly rational till now. Like the agents are being rational. They can see up to infinity. They can see every node of the tree. This is an assumption which we are making. This is a very strong assumption, actually speaking. Let's talk about poker now. Instead of getting actual poker, have anyone played Marvel Snap? It's okay, you don't need to. I'll give a, you don't need the rules, you just need the betting mechanism of this game. Yeah. There were advice given in Marvel Snap, never boomer snap. Boomer are old people, and old people are famously bad at gaming. Whatever boomer snap. Basically, you start a match wagering 1 point, and you can quote unquote snap to double your wager at any point. If you reach the last round of the game automatically doubles the wager. And if you snap on the final turn, you are getting your wager 4 times, 4x. So why boomer snap is snapping on the last turn? Why would someone boomer snap? Like why are there so many people who will just criticize you like anything if you boomer snap in this game's competitive meta? Yep. Sir, but let's say you're winning. So now you just 4 times the thing, right? So now you get a lot of money. Yes. Okay. The other player is just faulty. Yeah, could be. That's not the real reason, but yeah. So why could we not be? Even in poker, it's normally advised not to go all in or bet very aggressively on the last round. Why? No, people let's say you bet aggressively, people may have to just fold. Why will you not do it? Like, why is this a conventional advice given on these sides? Let's see. Suppose both players are perfect. They can see each other's cards. They are perfect probability computers. They know everything about the game. Very, very unlikely fact. But let's say this is true. There are two players A and B. The game is zero sum. So B's payout is negative of A's payout. The stake is initially set to 1. Both players know the probability of A winning, which we'll call P win. Probability of B winning is just 1 minus P win, right? The nodes of the decision tree are A can either call, fold, or raise. Call is just being on like 2x. Fold is saying, yeah, I don't want to play this game anymore. So call is just being on 1 wager. Fold is saying, I don't want to play this game anymore. And raise is, well, going 2x. And B can either call or fold based on what happened last turn, right? So let's see what happens. Yeah, I'll have to make the tree. we are considering two cases. One where you just raise to 2, right? Huh. Both of them have. Assume that they have infinite amount of money. Won't really matter. Even if you assume finite. Within the scope of the game, they have infinite. They have nothing all in here, right? You can just, like, Marvel Snap does not have that feature. If you remain at 1x1, what happens? Let's say the other guy just calls or folds. If it's 1x1, your probability of winning was p win. So there's a p win chance you get out with 1. And I don't need to write the other probability, right? It will just other side because it's just negative of this. If you end up losing, they just win. That's all really going to happen. If they fold, first player just gets with 1 rupee because they just did not do anything. It was a call. Raise call for, yeah, 2 times p win. Correct? 2 times what you get. And if they fold, 2. If you fold, -1. Correct? This is our game tree setup. So please notice that, wait, p win -1, p win minus. Oh my god. Yeah, sorry. 4 times the amount, right? You get their money as well. And 2 times the amount because you get their money as well. And -1 because that's the money you wagered to begin with, correct? I just made a few ups and downs here. Yeah, works. Everyone agrees with the payout structure. So let me ask you, when will I, let's say I'm here, when will I call? When 2 into p win -1, when will my opponent do this? Please note, because it's a zero sum game, opponent is just minimizing my things. If they minimize me, they're maximizing theirs, right? You can assume that. So them, yeah. Correct. They'll, if I called and they called, they need to just have it less than half, and they'll correct. Player B will call and less than half. Okay. Actually, I will not write that. Okay. What about when will they, if I raise, when will they do anything? Again, half. And if I fold, why will I fold? Basically speaking. So yeah. So if my probability is higher than half, I should raise because I get more money when I raise. Correct? So this seems not incorrect, right? We can agree that this does not seem incorrect. We can repeat the analysis with doing a bet into 4, and we'll see that something like this happens. Raising 4x is better than raising 2x. And this plateau happens because after one point they just start folding. Yes. Yeah, something will go wrong because of that. Correct. So why is the boomer snap bad? Because you're correct. We made a very strange assumption that everyone knows everything. That's true. That's untrue for every card game on this planet about. Of course, it's not a perfect information game. We are not playing chess. Chess is a perfect information game. This is not. Opponents cannot see cards in your hand. Additionally, players are not perfect computers. They may misjudge the situation, miscalculate p-win, which can also be interpreted as hidden information. And given your deck of cards is also secret, there's way too much information. Let us say there's a noisy signal called p cap. What is this signal? P cap will be in the range of p plus epsilon to, sorry, p minus epsilon to p plus epsilon. Let's say there's some error range uniformly distributed for both of the players. Why can I make this assumption of both the players here? Okay, both will have it in epsilon. Any guesses? No, but why can I assume that they have similar error ranges? Yeah, exactly. Normally we match by skill issue, so we'll take that. we are taking this unbiased because even if unbiased, like the expected value if you get the correct thing, because it's just uniformly distributed, right? They could get the same amount. Who knows? P cap. Yeah, depends. Like it could happen. What will happen if, with perfect information, 50 to 75% you were calling and then you were folding after that because you are losing too much money then. Correct? What will happen when there were hidden information? There were mix of things happening here based on what P cap did you get. Correct? Which is weird, right? Because this small mix will cause a bit of issues here. Greater the error, favors the raiser. As you can see, as the error increases, you are better to raise, right? Hidden information, and we get the boomer snap. This small area is where you shouldn't raise 4x. Let the 2x thing happen. Don't raise 4x. Could anyone give an intuitive explanation of why? Like, let's say we do not. Let's say there's a boomer. Let's say my dad is playing Marvel Snap. How do I explain my dad that you do not have to snap on the last turn without needing to explain him game theory? The point is, if you boomer snap, there's a chance your opponent just folds. They just fold. They don't raise, they just fold. They don't lose that much money on a fold, right? They'll just fold. Why not? They fold, they don't have to raise the amount. So they just fold and lose the rest of the remaining money. You don't get much. Instead, if you don't snap, you let your opponent feel that you don't have that good of a probability of winning, put in there too, and lose the money. Or whatever this game, they call it Tesseract in this game. But yeah, you just lose the money. Poker, mein, this is the idea that you should try to give your opponent the rope to hang themselves. Just enough rope to hang themselves. Notably, they suggest that they have a correct time to boomer snap. When your probability of winning is slightly just above 50, you can boomer snap and make it feel that your probability of winning is much higher. They have a time and place for this. And if you go to the competitive scene, you'll see some world-class players boomer snap once in a while. This is why they do it. But this is also not a complete model. What are some hidden assumptions and simplifications we are making? Yeah, here also you are doing the same thing. Boomer snap is raising 4x. 2x, the game will automatically force you to raise on the last turn. But if you voluntarily go and say I'm raising 4x, maybe it's like telling the person that you have I have a very good hand. Yeah. Yeah. Correct. That comes to the first point, signals. Some of these things are the signals. Some, like your brain develops signals, right? Someone betting like this is maybe a signal that they don't really have a hand. We will not talk about signaling, but the seminal paper on signaling is called Spencer's Education Game, where he talks about how education is like giving a signal to employers. It's a controversial paper, but the guy got a Nobel out of it, so who am I to judge? There's also an informational asymmetry, right? Let's say someone is a great deck builder. They have a great deck, but they're not very good at judging winning positions. So they can be at the similar skill level, but still not have the same epsilon term, right? We have also not talked about that. Often the other part is, let's say you have created a winning board state, and the other guy just have a lot of cards to do one last combo on the end turn. We still cannot talk about that. Again, this is again done by the Agarwal model called market for lemons, which is lemon selling market or something weird. What? Did someone say something? Yeah. Which book? Yeah. Oh, okay. I did not know. Oh, interesting. Interesting. Yeah. There was also something called rave errors. That let's say someone just raves out for fun or just irrationally raving. Maybe it's their last game and they want to do some fun. Multiple turns. Here is another thing. Marvel Snap, you could raise money at any point. There were 6 rounds before. Why did you raise it at the last round? Maybe there was never a point where you wanted to raise it. Maybe something else, right? Again, this is similar to the signaling point. That why would you suddenly bet a lot of money in the last round of poker? You had multiple rounds before that when the river was coming. Why did you not bet then? Weird. And for finally, curiosity calls. Sometimes in tournaments, players just do some strange things in the early rounds to try to guess the other player strategies. Note Spence and Akerlof along with Stiglitz got the 2001 Nobel for the above-mentioned things. Other than that, such analysis comes under something called poker theory. This is an actual theory people work in. MIT have an open courseware on this. It's good. And finally, we come to the thing we were all here for, bubbles. How late am I? Shelling. Okay, yeah. There are two towns, E and W. There are two types of people, plus F and minus F. Every town has 1,000 people. Every town can hold 1,000 people. Utility function of plus F and minus F based on population of people of the same sign in the town. We can let the utility function be this graph. Is the graph visible? Yeah. As we can see, people are not very finest. People are not like, nahi, I want 100% people to be like me. In short, they're even demanding a little bit of diversity. They're saying, I'll be happiest if there are 50% people are like me and 50% are of the other type. They just prefer not to be in the minority, which is justifiable, I think. No one wants to be a minority where they live to some extent. What do you think happens here with this people? What happens when I let's say we play a game every turn, each person decides which town they wish to live in simultaneously. If more than 1,000 people choose a town, a random 1,000 of them are allowed to be there and the others are sent to the other town. Yeah. So they will get segregated. Yeah, that's a Nash equilibrium. Because once you reach segregation, if everyone remains at the same town, a minus have no incentive to go to the plus town. They'll be almost zero, right? So their graph is bad. Correct. Yeah, there was 50-50 Nash equilibrium. Exactly. So the 50-50 Nash equilibrium in some ways is a bit wobbly of equilibrium, right? Like it's very easy to break the 50-50 Nash equilibrium. A few radical people and our unity, diversity, integrity, everything goes away. And we get segregated. What do we observe? As we can see, people are not finest and they just got segregated because of fines. This is called a Schelling model, which brings up the possibility that segregation does not imply people being racist or finest or whatever the word is. It was proposed by Thomas Schelling, who shared a Nobel with Robert Omen. While not relevant here, Omen's work is on peace and war, one of my favorite things ever. Coming back to the model, what are the Nash equilibriums? I think we got 3 Nash equilibriums. All plus 2 east town, minus 2 west town, all minus 2 east town, plus 2 west town, and 50-50. This is stable. One person changing does not cause issue, but a coalition of people changing causes issue. This is called a non-coalition proof Nash equilibrium. These are studied in something called Shapley theories, where we talk about how big of a coalition is needed to break a equilibrium to something else. Okay, yeah. There is how much time? 5 minutes are left. 5 ठीक है हो जाएगा. अच्छा. Okay, I'll try to run. Okay, coming back to the model, what are the Nash equilibriums here? There are 2 more which we are missing. Obviously, the hardest ones to observe are if everyone tries to go to E. Let's say E is like a very good city, a utopia, and West is a city where a dictator is ruling with an iron fist. So everyone just wants to go to E, and by the law of just choosing 1,000 people, we are getting somewhat of an equilibrium situation. And the last one is not something which really happens. It's induced by our method of modeling, just making the populations constant. Yeah. So the point is, in our graph, like this one, even a little, even if I just, instead of keeping it 50-50, if I keep it 30, like you just want 30% people to be like you, will still get segregated. Why is this happening? It's because we are saying that people know everything about their city and the population ethnics of the other city. That's not really realistic, is it? Do you know everything about your city? Probably not. In reality, we can only be sure about our neighbors. Schelling original model was simple. It was a cellular automata, n by n grid. If k% neighbors are of a given color, you just move to another square, if less than k%, then you just move to another square which seems more feasible, more likable. And this will keep going. And agent would not move unless this condition was triggered. While formal proof came quite late, even 33% was enough to cause segregation. So there were resources for this called Weihart and Nick Casey's polygons. I think some of you might have seen this one. If you haven't, it's very good. It won't take more than 5 minutes to read. Yeah. We didn't bring automata as it's older, and much of its data is not proven as of now as well. But secondly, ever since social media have got more common, and we are seeing a resurgence of casteism and segregation, right? Well, social media does make our model seem less hypothetical, as we do have some partial information on ethnic places. But one has to ask, what does all of this have to do with bubbles? I started bubbles, right? Well, I'll have to rush through this part. Yeah, this section is based on this work by CMU, and the trading equivalent was drawn by me and Ryan Bhaiya. Trading is just like fashion. People want to wear trendy styles, but similarly in market, you want to be on the momentum when something is rising. However, if you innovate and adopt a new trend, just be a bit unique, suddenly you create your own trends. In trading, similarly, just before trend reverses or identifying an undervalued asset gets you money. Yeah. So this is some utility function. We'll not go into it. Here the only thing is, this is the mean of the people. So this is the mean of the people. This is your choice. So we are saying that you get utility by being close to the mean, and this is the number of people who are doing the same thing, and this is just some parameter. But you also lose utility by, like, you want to be close to the people, mean, but you don't want to be completely. There are two conflicting ideologies here, right? You want to be fashionable, but you also want to innovate. Okay, this is just me telling that in very formal fashion. Ignore that. Yeah. So yeah, every player keeps changing the XI to get better payoff continuously. We can, as it turns out, we can prove that this converges to a equilibrium always. But that is strange, right? We don't see the one fashion trend being like only some people will follow it, no one else will follow it. This does not happen. The trends just keep coming and going. So what are we missing really? Similar to Schelling model, we don't really know what everyone else is doing. We can only be sure about our neighbors. These are our neighbors. Nita. And once we know about our neighbors, Nita, use the set of your neighbors of you. Once you know this much, there is no Nash equilibrium. The proof is by construction. Can anyone just guess a construction proof here? Two people, there will be a Nash equilibrium. Both of them doing different things. Three people is your answer. Exactly. Triangle. This guy observe. A is observing B, B is observing C, C is observing A. You can prove that no two color graph coloring exists, and hence this will always not have a Nash equilibrium. We can, with only local interaction for a social network, perpetually changing identity expression and popularity cycles become possible. However, our construction was highly pedagogical. Sorry, highly, I think that's the wrong word for it. Highly pathological, I think the word should be. It does not tell us whether complex social dynamics typically emerge from our model when people are connected by realistic social networks. While obtaining a formal proof is much harder and as of now open, this is a very recent paper, 21, we can use computational modeling to get the idea. We need to make some changes for financial market. The changes is, I will not do the complete thing because, yeah. Here in financial market, this is the mean thing, the mean of the entire population. The stock price is actually a global variable, right? So that does not base on your neighbor. Your differentiation thing bases on your neighbor. That's all. On stock markets, yeah. So this was a randomly generated 100 graph, 100 member graph. Every person had 200 choices from 0 to 199, white to black. If you look at the graph, you can notice that all graphs have basically clustered into maybe 3 or 4 choices, right? White, gray, black, sometimes 2 shades of gray. This was repeated around for 100 such graphs. Creating such realistic graph is somewhat computationally expensive. You are not randomly creating. I think something called the Gilman's algorithm was used for it. And this is what we found. In a huge number of trials, it was non-convergent. So we also noticed starting with 200 choices, the individuals have chosen the same 3-6 identities. Everything other than that came as a fad went away. This is true on both sides. Despite many trends coming and going, people still wear polos. I think a bunch of you are wearing polos at this moment. Similarly, despite market up and down, Tata, ITC, etc. are always dependable investments. Finally, now we can understand the role of networks and location interaction. Popularity cycles, bubbles, perpetual change, bursts, and novel expression, arbitrage of social identity should be expected when people observe their neighbors in realistic directed social networks and care about being unique, not being the last person holding the dollar, as well as fitting in, riding the momentum. Conclusion. There's this great book called The Intelligent Investor. It's considered the hallmark of investing rationally. It has a page called Words of Warning, and it tells whenever you hear things like this, you should run far away. Our proprietary computer model, trust me bro, monthly returns, you should focus on performance, not fees, don't you want to be rich? We hear this about every second thing nowadays. So is the greatest book on investing just wrong in today's century? Over centuries, we have seen people, smart people, rich people, entire economy fall for the same trap. Whether it was tulip, .com stocks, crypto, or AI stocks at this moment. Companies were just claiming that we use AI. Spotify says we use AI to make our playlist. Bro, you did that before AI boom. They have a basic algorithm. It's a co-product vector something. The game have always been the same. Hype inflates, logic evaporates, and then boom, gravity. So what is the lesson here? Markets aren't rational, people aren't rational, but you can choose to be. Markets were somewhat irrational in the fact that they want to be different. That lambda parameter is introducing a bit of irrationality here. Every bubble have a max stupid point. When prices stop being about value and start being about speculation, you are just playing chicken with reality. Don't be the last fool holding the bag. Rationality is not profit. Just because you are making money doesn't mean you are smart. We can see that with one very particular person who just bought a very big social media fight and is losing a lot of money. I'll not take any names. The smartest people in history have lost fortunes thinking they're invincible. Newton lost a lot of money on alchemy. The crowd is often wrong, but doesn't mean you should be contrarian for the hell of it. Sometimes the herd is running towards the cliff, sometimes they've actually found gold. Your job, know the difference. Understanding the game is more important than playing in. Everyone wants to win, but few understand why the game works the way it does. Study incentive, study behavior, that's where the real power is. I am sure some of you want to tell me that crypto is the future, AI is not a bubble, or have fun staying poor. And I want to tell you to be aware. But if you feel this was too much ado about nothing, well, I have a tulip to sell you. And yeah, if you want to take another thing, please study these subjects. Very little people are studying it in India. Please do so. Yeah. Other than that, thank you. I'm done.